Tonight, we're going to dismantle a picture. The picture most people carry of what a galaxy is, where it sits, what it is made of, how it behaves, and what role it plays in the structure of the universe. That picture is not completely wrong. It is approximately right in the way that a street map drawn from memory is approximately right. Useful for navigating within its limits, but dangerously misleading the moment you rely on any detail too closely. The details are where galaxies become genuinely extraordinary, and the details are almost universally the opposite of what intuition suggests. Galaxies look like compact, contained things. They are not contained. They extend far beyond their visible edges, held together by matter that produces no light. They look like isolated objects floating in empty space. They are not isolated. They are embedded in a cosmic web of dark matter and hot gas that connects everything to everything. They look static or slowly rotating. They are violent. They cannibalize each other on time scales of billions of years, and many of them contain engines at their centers more energetic than the combined output of hundreds of billions of stars. The standard image of a galaxy, a pinwheel of glowing stars and gas, captures roughly 5% of what the object actually is. The rest is dark matter, diffuse gas, embedded structure, and history. If you could see a galaxy in full, including all its components, all its invisible mass, all its connections to the cosmic web surrounding it, you would not recognize it from the textbook picture. Understanding what galaxies actually are requires dismantling several assumptions that are so deeply embedded in popular presentations of astronomy that they feel like facts. The assumption that what we see is what is there. The assumption that the edges of a galaxy correspond to something physical. The assumption that galaxies are old and settled structures that formed long ago and have been sitting passively ever since. All of these assumptions are wrong, and understanding why they are wrong is the best path into understanding what galaxies genuinely are. By the end of tonight, you will have a fundamentally different picture of the galaxy you are inside, of the 2 trillion other galaxies in the observable universe, and of the framework that organizes all of them. Not a complete picture, because galaxies are still producing scientific surprises at an impressive rate, and several major questions about their formation and behavior remain unanswered, but an honest picture, one that accurately represents both what is known and where the remaining mysteries sit. If this kind of genuine, deep engagement with the science is what you're looking for, subscribe and leave a like. It helps this channel reach people who want more than the surface version. Now, let us start from where most people begin, with what everyone once thought galaxies were. The misconceptions run deeper than simple ignorance of facts. They are structural. They reflect the way the visible universe presents itself to observation. A galaxy image produced by even the finest telescope shows what the light shows, and light comes from the stars and hot gas that represent the energetically active minority of the galactic system. The dark matter halo, the circumgalactic medium, the cosmic web of dark matter filaments connecting galaxies. None of these contribute photons to telescope detectors in the wavelength ranges most commonly used for deep imaging. They exist and they dominate, but they are invisible to the direct gaze. This is why the revision of our understanding of galaxies has been so sustained and so dramatic over the past century. It is not that earlier astronomers were careless or intellectually limited. It is that each new observational capability, each new wavelength window opened, each new instrument deployed has revealed a component of the galactic universe that was invisible to all prior observation. The radio sky showed jets and lobes from the active galactic nuclei that had no optical signature. The X-ray sky showed hot gas and galaxy clusters, invisible at every other wavelength. Infrared surveys showed dust-enshrouded star formation, invisible optically. Gravitational lensing showed mass concentrated where no light was produced. The history of galactic astronomy is a history of being surprised by what the universe hid. The surprises are not finished. Multiple major open questions about Galaxy formation and evolution remain unresolved. How exactly do galaxies stop forming stars? What is the dark matter made of? Where precisely are the missing baryons? Why do early universe galaxies look more evolved than the standard model predicts? Each of these questions, and the observations that will eventually answer them, will add further dimensions to the picture of what a galaxy actually is. The systematic study of galaxies is barely a century old, and the picture of what they are has been revised repeatedly and dramatically since the first serious attempts to understand them were made in the early 20th century. What came before, both the popular and scientific understanding, was not merely incomplete. It was wrong in foundational ways that illuminate how difficult it is to interpret diffuse patches of light in the night sky without the theoretical and instrumental tools that eventually allowed their true nature to be revealed. In the 18th and 19th centuries, astronomers cataloged numerous diffuse smears of light in the sky, distinguishing them from stars by their extended appearance and from planetary nebulae by their lack of central stars and by their often regular, elongated shapes. The Great Nebula in Andromeda was among the most prominent of these objects, visible to the naked eye on dark nights and appearing in telescopes as a bright oval glow with a bright center fading smoothly to the edges. Immanuel Kant proposed in 1755 that these nebulae might be island universes, systems of stars too distant to resolve individually into separate points of light. Kant's hypothesis was speculative, made without any observational evidence for the actual distances involved. For the next century and a half, the nature of the spiral nebulae was genuinely uncertain. The debate centered on whether they were relatively small, nearby structures within or near our own galaxy, or whether they were distant, separate systems comparable in scale to the Milky Way. The Milky Way itself was not well understood, but estimates of its size had been growing through the 19th and early 20th centuries. If the Milky Way was a large system, could the spiral nebulae be similar systems at large distances? Or were they smaller objects in the nearby cosmic environment? The debate was not merely academic. It depended on measurements that pushed the technical limits of the era. Attempting to measure the distances to spiral nebulae without reliable distance indicators was essentially impossible. The spectral measurements available showed that the nebulae had spectra similar to stars, consistent with being collections of stars, but the resolution needed to see individual stars in even the nearest nebulae was beyond any telescope then in existence. What everyone assumed, regardless of which side of the debate they occupied, was that the nebulae were straightforwardly what they appeared to be: compact collections of material, bounded, self-contained, essentially complete as seen through the telescope. Nobody imagined that what was visible might represent a small fraction of the actual extent of these systems. The Great Debate of 1920, a formal public debate held at the Smithsonian Institution in Washington between Harlow Shapley and Heber Curtis, crystallized the competing views. Shapley argued that the Milky Way was a much larger system than previously believed, and that the spiral nebulae were relatively small clouds within or near the Milky Way. Curtis argued that the Milky Way was smaller, more like the sun-centered disk of earlier tradition, and that the spiral nebulae were external galaxies comparable in scale. Both men were right about some things and wrong about others. Shapley was correct that the Milky Way was large and that the sun was not at its center, discoveries he had made by studying the distribution of globular clusters. But he was wrong about the nature of the spiral nebulae. Curtis was wrong about the sun being near the center of the Milky Way, but right that the spirals were independent external systems. The debate could not be definitively resolved at the time because the key observational tool, reliable distance measurements to the nebulae, was not yet available. What both participants shared, and what both got wrong, was the assumption that the visible boundaries of a galaxy corresponded to the actual extent of the system. The idea that most of a galaxy's mass might be invisible that the edges of the stellar disk might represent only the inner fraction of a much larger gravitational structure, was not on the table. It would not be on the table for another half-century. The question of the nature of spiral nebulae was resolved decisively by one person, using one technique at one specific moment in astronomical history. Edwin Hubble, working with the new 100-inch Hooker telescope at Mount Wilson Observatory in the early 1920s, managed to resolve individual stars in the outer regions of the Andromeda Nebula. Among those stars were Cepheid variable stars, pulsating stars whose intrinsic luminosity is tightly correlated with their pulsation period. Henrietta Swan Leavitt had established this period luminosity relationship in 1908 from observations of Cepheids in the Small Magellanic Cloud, and it provided a way to convert from the period of a Cepheid's variation to its intrinsic luminosity, which could then be compared to its apparent brightness to determine its distance. Hubble measured the periods of the Cepheids in Andromeda and calculated a distance of approximately 900,000 light-years, later revised upward to approximately 2.5 million light-years as the Cepheid period luminosity calibration was improved. Either way, Andromeda was not a small nearby nebula. It was a vast system of stars at a distance so enormous that the light we receive from it tonight left before our species existed. The great debate about the nature of the spiral nebulae was over. They were galaxies, each a system of stars comparable to or exceeding the Milky Way in size, and the universe was incomparably vaster than had been believed. This discovery is sometimes presented as simply establishing that galaxies are very far away. That framing understates how completely it restructured the conceptual landscape. Before Hubble, the question of how large the universe was had no clear answer, but the assumption was that it was not so much larger than the observable stellar system. After Hubble, astronomers understood they were dealing with a universe of practically unlimited extent, filled with billions of systems each containing billions of stars. The Milky Way was not the universe. It was one of countless islands in an ocean of nearly unimaginable size. But even this new understanding came packaged with assumptions that would later prove wrong. The galaxies looked like compact, bounded things, and they were treated as such. Dark matter was not yet known to exist. The cosmic web had not been discovered. The activity hidden in galactic centers had not been detected. The picture was larger than before, but it was still a picture of galaxies as essentially what they appeared to be, just at greater distance. Hubble's distance measurement to Andromeda was not without its complexities and subsequent refinements. The calibration of the Cepheid period luminosity relation that he used was later found to be systematically in error by a factor of roughly 2. The error arose from not recognizing that there are two distinct populations of Cepheid variable stars, and Leavitt's calibration, derived from one population in the Magellanic Clouds, was being applied to a different population in Andromeda. When Walter Body corrected this error in the 1950s, using the new 200-inch Palomar telescope, the distance to Andromeda doubled to approximately 2 million light-years, and all other extragalactic distance estimates were revised upward accordingly. This revision had immediate consequences for our understanding of the scale of the universe and the scale of individual galaxies. When Hubble's original distance was accepted, Andromeda seemed somewhat similar to the Milky Way in size. When the corrected distance was established, Andromeda was revealed to be significantly more distant and therefore physically larger than the Milky Way, or at least comparable in size. The history of successive distance revisions is a recurring feature of extragalactic astronomy and reflects the difficulty of establishing the absolute distance scale without circularity. The Cepheid distance method remains the primary first rung of the extragalactic distance ladder today, calibrated with much higher precision through Hubble Space Telescope and Gaia measurements. But even now, the absolute calibration of Cepheid distances is a subject of active research and is one of the primary sources of uncertainty in measurements of the Hubble constant, the rate of expansion of the universe. The philosophical significance of Hubble's discovery extended far beyond the technical question of the distances to the nebulae. It established definitively that the universe contains structures vastly larger than any single stellar system, that the Milky Way is one member of a cosmological community of comparable objects, and that the universe's physical scale is so large that light from the nearest comparable system takes over 2 million years to reach us. The night sky, which had been interpreted for millennia as a finite dome of fixed stars, was revealed to be a window into an effectively unlimited space filled with billions of systems each as complex as the one we inhabit. Given the history of misconceptions, it is worth attempting a precise definition of what a galaxy is before working through the specific ways that standard intuitions fail. This is not as simple as it sounds, because galaxies do not have sharp edges, do not exist in isolation, and are not the only structures at the relevant mass scales. The functional definition is something like this. A galaxy is a gravitationally bound system containing stars, gas, dust, and dark matter, with a total mass typically between 1 million and 1 trillion solar masses, and with a size ranging from a few hundred light years for the smallest dwarf galaxies to hundreds of thousands of light years for the largest giants. This definition is broad enough to encompass the enormous diversity of galactic morphologies and sizes that observations have revealed, from the ultra-faint dwarf spheroidal galaxies with only a few million stars to the enormous elliptical galaxies at the centers of rich clusters containing several trillion stars. What the definition does not convey is the character of galaxies as dynamical systems. Galaxies are not static structures. They are in continuous motion, with stars orbiting on timescales of hundreds of millions of years, gas flowing in from the intergalactic medium and out through stellar feedback and galactic winds, and the overall system evolving on timescales of billions of years through mergers, interactions, and the continuous cycle of star formation and stellar death. The galaxy you see in a telescope image is a snapshot of a dynamical system in ongoing evolution, not a finished product. The definition also does not capture the fact that what we observe in optical light, the stars and glowing gas that produce the visible image, represents only a fraction of the total galactic system. Dark matter, which by current estimates constitutes roughly 80 to 90% of the total mass of a typical galaxy, does not emit or absorb light at any wavelength. It is detectable only through its gravitational effects. Including dark matter in the definition of what a galaxy is changes the picture dramatically. The stellar disk that produces the visible image sits inside a much larger, roughly spherical, dark matter halo that extends far beyond the visible edges of the galaxy. The mass range of galaxies spans an extraordinary 10 to 12 orders of magnitude. The smallest known galaxies, called ultra-faint dwarf galaxies, and discovered primarily as satellites of the Milky Way and Andromeda in the past 2 decades, contain as few as a few thousand stars, and have total masses of perhaps 1 million solar masses, including dark matter. The most massive galaxies, the brightest cluster galaxies at the centers of the largest galaxy clusters, contain several trillion solar masses in stars and are embedded in dark matter halos of perhaps 100 trillion solar masses. Between these extremes lies a continuous population with no sharp divisions except those imposed by the observational difficulty of detecting the faintest systems. The morphological diversity of galaxies, their variety of shapes, is one of the most visually striking features of any deep field image. Spiral galaxies with their majestic arms, elliptical galaxies with their smooth, featureless profiles, irregular galaxies whose shapes defy simple geometric description, often the result of tidal interactions with neighbors or ongoing mergers. Lenticular galaxies that have the disk of a spiral but lack the spiral arms, thought to have had their star formation quenched at some point in their past. Ring galaxies produced by head-on collisions. Polar ring galaxies were a ring of stars and gas orbits perpendicular to the main disk. This diversity is not random. It reflects the different formation histories and environments of galaxies. Spirals tend to live in less dense environments and to have had relatively calm merger histories. Ellipticals are concentrated in the dense cores of galaxy clusters and bear the marks of many major mergers that have destroyed the disk structure and scattered stars into the smooth, spheroidal distribution. Understanding morphological diversity means understanding galactic history. The stellar mass-to-light ratio is a critical parameter that bridges the observable galaxy luminosity and the inferred galaxy stellar mass. A galaxy dominated by old red stars has a higher mass-to-light ratio than one dominated by young blue stars, because old stars produce less light per unit of stellar mass. The ratio depends sensitively on the age, chemical composition, and initial mass function of the stellar population, and determining it accurately for distant galaxies requires detailed modeling of the spectral energy distribution. Systematic errors in the mass-to-light ratio propagate directly into estimates of stellar mass, and therefore into any comparison between observed galaxy masses and theoretical predictions. The Milky Way presents a particular challenge for cartography because we are inside it, making any attempt to determine its overall structure equivalent to trying to draw a map of a city from a location in one of its neighborhoods, unable to step outside and see the whole thing at once. The result of this observational constraint is that the Milky Way's large-scale structure was determined slowly, incompletely, and with significant errors that persisted until relatively recently. The classic picture of the Milky Way as a flat disk of stars, perhaps 100,000 light-years in diameter, with a central bulge and spiral arms extending outward from the center, is not wrong, but it is significantly incomplete. The true structure is more complex than this in several ways that matter for understanding what galaxies are. The disk is not flat. Warped is the correct description. The outer Milky Way disk curls upward on one side and downward on the other, a feature called the galactic warp that has been known for decades and whose origin is still debated. One hypothesis attributes it to the gravitational influence of the Large and Small Magellanic Clouds, the two companion galaxies orbiting the Milky Way. Another attributes it to a tilted dark matter halo. The warp is not a minor perturbation. In the outer disk, stars can be displaced from the average plane by several thousand light-years. The spiral arm structure is also more complex than the simple four-arm picture that appears in many textbook illustrations. The Milky Way appears to have two major spiral arms, Perseus and Scutum Centaurus, with additional shorter arm segments and spurs. The Sun is located in one of these shorter features, the Orion arm or Orion spur, which is not a major arm but a connection between two of the larger ones. The characterization of the arm structure has required painstaking observation of masers, young stars, and molecular clouds distributed throughout the galactic plane, penetrating the dust that obscures optical observations, and the picture has been repeatedly revised as new data from radio and infrared surveys accumulated. The central bar is another feature that was established only relatively recently. The Milky Way is not a pure spiral galaxy. Like many spirals, it has a bar-shaped stellar structure extending from the center, with the spiral arms emerging from the ends of the bar rather than from the center directly. This makes it a barred spiral, classified as SBBC in the morphological scheme. The bar was confirmed observationally through infrared surveys in the 1990s, and its precise length and orientation are still refined with new data. The discovery that the Milky Way's disk is not simply flat, but warped and flared at large, radii has implications beyond simple cartography. The warp is a dynamical feature that provides information about the mass distribution of the dark matter halo and about the recent gravitational history of the galaxy. A dark matter halo that is slightly misaligned with the stellar disk can produce a persistent warp through its gravitational influence. The infall of satellite galaxies can also produce warps as they interact tidally with the disk. Distinguishing between these mechanisms requires detailed three-dimensional mapping of stellar positions and motions, work that the Gaia satellite is making possible for the first time at the relevant spatial scales. The flaring of the disk at large galactic radii, a systematic increase in the vertical thickness of the disk as radius increases, is another feature that has been characterized with increasing precision through infrared surveys that can see through the dust to map the stellar distribution across the disk. At the Sun's galactic radius, the disk has a scale height of roughly 1,000 light-years for the thick disk component and roughly 350 light-years for the thin disk. At twice the Sun's galactic radius, these scale heights are significantly larger, and the distinction between the disk and the halo becomes progressively less sharp. Understanding the true three-dimensional structure of the Milky Way is also essential for understanding the distribution of dark matter within it. The rotation curve of the Milky Way, measured from the orbital velocities of gas clouds and stars at different radii, constrains the total mass within each radius. Fitting dark matter halo models to this rotation curve requires accurate knowledge of how the visible mass is distributed, since only the residual after subtracting the visible mass contribution tells you what the dark matter alone is doing. When astronomers describe a galaxy's size, they typically quote a specific metric, the radius that contains half the total starlight, called the half-light radius, or effective radius. This is a useful and standardized measurement, but it has a built-in limitation that creates a systematic misunderstanding about how large galaxies actually are. The half-light radius captures the compact, bright central region where most of the stars and most of the visible light are concentrated. It says almost nothing about how far the galaxy's influence and its associated matter actually extend. The Milky Way's disk, where most of its stars reside, extends to roughly 25,000 to 30,000 light-years in radius under conventional definitions. That already sounds large, but the stellar disk is embedded in a dark matter halo that extends to perhaps 600,000 to 1 million light-years. The virial radius of the Milky Way, which defines the extent of the dark matter halo within which material is gravitationally bound to the galaxy, is somewhere around 650,000 light-years. The stellar disk, which is what the visible image of the galaxy shows, occupies roughly 5% of this total radius. The object you see in a photograph of a spiral galaxy is the bright center of a vastly larger dark structure, the diffuse stellar halo, a component of stars distributed in a rough sphere around the stellar disk and extending to perhaps 100,000 to 200,000 light-years, is intermediate between the disk and the dark matter halo. It is made of stars, unlike the dark matter halo, but it is faint and diffuse enough that it contributes little to the integrated starlight of the galaxy. It contains roughly 1% of the Milky Way's total stellar mass, despite its enormous spatial extent. Even the stellar disk extends further than the bright region visible in images. Deep photometric surveys of nearby galaxies have detected stellar material at surface brightnesses far below what is visible in typical exposures, revealing that the disks of spiral galaxies continue to much larger radii than their bright central regions suggest. The outer disk is not sharp-edged, but fades gradually into the stellar halo and eventually into the intergalactic medium. The existence of stellar streams extending to enormous distances from the Milky Way's center illustrates how far the galaxy's gravitational reach extends. The Sagittarius stream, produced by the tidal disruption of the Sagittarius dwarf galaxy, wraps nearly completely around the sky and reaches to distances of 200,000 light-years from the galactic center. Stars at those distances are gravitationally bound to the Milky Way, tracing orbits that take several billion years to complete. They are part of the Milky Way by any reasonable definition, yet they are so distant that they would be outside the disk radius quoted in most textbooks. Deep photometric surveys of the sky have revealed a population of stars at the extreme outskirts of the Milky Way, at distances of 100,000 to 300,000 light-years from the center, that appear to form a thick, irregular sheet, sometimes called the outer stellar halo, or the Milky Way's outer disk. Whether this structure is continuous with the main disk or represents a distinct structural component, perhaps material accreted from satellite galaxies, is still being investigated. Its existence further complicates any simple characterization of where the Milky Way ends. The same issue applies to other galaxies. When deep imaging surveys have been applied to nearby spiral and elliptical galaxies, they reveal vast, faint envelopes of stars extending to multiple times the effective radius usually quoted as the galaxy's size. These stellar halos, built up from the disrupted debris of swallowed satellite galaxies, tell the story of each galaxy's merger history. Mapping them in detail is among the primary scientific goals of the next generation of wide-field survey telescopes. The discovery that most of the mass of a typical galaxy consists of matter that emits no light and cannot be directly detected by any instrument is among the most significant and most unsettling in the history of astronomy. It is also a discovery that was resisted for decades after the evidence first appeared, because accepting it required abandoning the intuition that what we can see is what is there. The first clear evidence came from measurements of the rotation curves of galaxies. If a galaxy's mass were concentrated in its visible stars and gas, distributed roughly as the light suggests, then the orbital velocities of material at different galactic radii should follow a pattern similar to the planets in the solar system. Material farther from the center should move more slowly, because the gravitational force pulling it inward decreases with distance. This prediction was tested in the 1970s by Vera Rubin, Kent Ford, and their collaborators, who measured the Doppler shifts of emission lines in spiral galaxies to determine orbital velocities at different radii. The results were unambiguous and incompatible with the visible mass prediction. The rotation curves were flat. Orbital velocities did not decrease at large radii. They remained roughly constant far out into the disk and beyond. The only interpretation consistent with flat rotation curves is that the total mass enclosed within any given radius continues to grow, even in regions where no stars or gas are visible. There must be matter beyond the visible stellar disk, distributed in a roughly spherical halo, with a density that decreases with radius in exactly the way needed to keep the rotation curve flat. This is dark matter. The amount of dark matter required is not small. For a typical spiral galaxy, the dark matter halo contains roughly 5 to 10 times as much mass as all the stars and gas combined. The visible galaxy, everything you can see in any telescope image at any wavelength, represents only 10 to 20% of the total mass of the galactic system. The remaining 80 to 90% is dark matter, detectable only through its gravitational influence on stars, gas, and light. The evidence for dark matter is not confined to rotation curves. It comes from multiple independent observational approaches that all converge on the same conclusion. Gravitational lensing, the bending of light from distant background objects by the mass of foreground galaxies and clusters, provides a way to measure the total projected mass distribution independently of any assumption about the nature of the mass. Strong gravitational lensing, producing Einstein rings or multiple images of background quasars, gives precise constraints on the mass enclosed within specific radii. Weak gravitational lensing, producing coherent but tiny distortions in the shapes of large numbers of background galaxies, maps the total mass distribution over extended regions. In all cases, the inferred mass significantly exceeds the visible mass. Galaxy cluster dynamics provide another independent line of evidence. Within galaxy clusters, individual galaxies orbit the cluster center at velocities determined by the total mass of the cluster. If the total mass were only the mass in stars and the hot intracluster gas visible in X-rays, the galaxies would be moving too fast to remain gravitationally bound, and clusters would be flying apart on timescales much shorter than the age of the universe. The observed velocities require several times more mass than is visible. The same conclusion emerges from detailed hydrostatic equilibrium modeling of the hot intracluster gas. The gas pressure distribution implies a total gravitational potential much stronger than visible mass alone provides. The bullet cluster, a system of two galaxy clusters that have recently passed through each other, provides perhaps the most visually compelling evidence. The collision has separated the visible components. Hot gas, revealed by X-ray observations, has been slowed by gas-gas pressure and sits between the two clusters, while the galaxies have passed through relatively unimpeded. The dark matter halos, revealed by gravitational lensing, closely follow the galaxies rather than the gas, demonstrating that dark matter does not interact with itself or with ordinary matter, other than through gravity. The mystery of what dark matter actually consists of, at the particle physics level, remains one of the deepest unsolved problems in physics. The observational evidence establishes robustly that dark matter exists, that it is not made of any known particle, and that it behaves as a pressureless fluid on cosmological scales, clustering under gravity, but not interacting electromagnetically. The leading theoretical candidate classes include weakly interacting massive particles predicted by supersymmetric extensions of the Standard Model, axions originally proposed to solve an unrelated problem in quantum chromodynamics, and various other hypothetical particles. Despite decades of increasingly sensitive laboratory searches, no dark matter particle has been directly detected. At the center of the Milky Way, at a distance of approximately 26,000 light-years from the Sun, sits one of the most extreme environments in the galaxy. Understanding what is there and how it was discovered requires navigating through the dust that makes the galactic center completely invisible at optical wavelengths, and into the infrared and radio observations that pierce the intervening obscuration. Radio observations in the 1970s and 1980s revealed an extraordinary concentration of radio emission from the galactic center, including a compact source called Sagittarius A star that showed characteristics inconsistent with ordinary stellar emission. The source was bright, variable, and extraordinarily compact, with an angular size smaller than what any known type of stellar object could fit within at the galactic distance. The evidence pointed toward a supermassive black hole, but establishing this definitively required tracking the orbits of individual stars near the center over many years. Two teams, one led by Reinhard Genzel and the other by Andrea Ghez, independently accomplished this using infrared adaptive optics imaging from large ground-based telescopes, achieving resolution high enough to track stars moving at thousands of kilometers per second in orbits passing within a few light hours of the galactic center. By 2002, enough of these stellar orbits had been measured to confirm that the central object was a black hole with a mass of approximately 4 million solar masses. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for this work. This supermassive black hole, Sagittarius A star, is now known to be dormant. It is not currently accreting material at a high enough rate to produce the luminous emission seen in active galactic nuclei. But its presence, and the evidence for it, was a revelation about the nature of galactic centers. Almost every sufficiently massive galaxy that has been studied in enough detail has been found to contain a central supermassive black hole with masses ranging from millions to tens of billions of solar masses. The presence of these objects at the centers of galaxies is not an exceptional feature of certain exotic systems. It appears to be a universal feature of the galactic landscape. The environment within a few light years of Sagittarius A star is extraordinary in ways that go beyond the presence of the black hole itself. The central molecular zone, a region roughly 1,000 light-years across, centered on the galactic center, contains an unusual concentration of molecular gas at elevated temperatures compared to molecular clouds elsewhere in the galaxy. The turbulence in this gas is higher, the chemical composition is more complex, and the conditions for star formation are quite different from those in the disk. Star formation in the central molecular zone has been happening, but in bursts rather than continuously, and the most recent burst produced a cluster of massive young stars, the Arches and Quintuplet clusters, only a few million years ago. Within the central few light years, the density of stars is extraordinary. The nuclear star cluster surrounding Sagittarius, A star, has a stellar density roughly 1,000,000 times higher than the solar neighborhood. Stars in this region orbit the black hole at speeds of thousands of kilometers per second. The environment is bathed in intense X-ray and ultraviolet radiation from the accretion events when material falls onto the black hole, as well as from the winds and radiation of the massive young stars present in the cluster, Sagittarius. A star is currently quiescent by AGN standards, but it was not always so. X-ray observations have revealed SGRA-OC's echoes, fluorescent X-ray emission from molecular clouds that were illuminated by a much brighter outburst from the galactic center roughly 300 to 600 years ago. The evidence suggests that even at this outburst level, SGRA-OC was not as active as the luminous quasars of the early universe. But the relics of even this modest past activity are still detectable in the surrounding gas clouds, providing a window into the intermittent history of activity at the center of our own galaxy. One of the most counterintuitive aspects of galaxy dynamics is the way that stars move within them, which is nothing like the planetary orbits that dominate our intuition about gravitational systems. Understanding this difference is essential for understanding why galaxies have the shapes they do and how they evolve over time. The solar system is hierarchical and dominated by a single massive object, the Sun. The Sun contains more than 99% of the solar system's total mass, and the result is that planetary orbits are essentially pure two-body problems. Each planet moves in a well-defined ellipse around the Sun, essentially unperturbed by the other planets over short timescales. The orbital periods are precise and the motions are predictable centuries in advance. Galaxies work completely differently. No single star dominates the mass of the galaxy. The gravitational field that any given star moves within is the combined field of hundreds of billions of other stars, plus the dark matter halo. This collective gravitational field is smooth on the scales relevant to stellar orbits, and the orbits of individual stars are not generally simple ellipses. In the disk of a spiral galaxy, stars follow roughly circular orbits, but with additional oscillations up and down through the disk plane and inward and outward in radius, producing complex rosette-like paths that never exactly repeat. The time scale for a star to complete one orbit around the galactic center varies with radius. The Sun, at roughly 26,000 light-years from the center, takes approximately 225 to 250 million years to complete one orbit. Stars at larger radii take longer. Stars at smaller radii take shorter times. This differential rotation means that any initial pattern in the disk, including the spiral arms themselves, would wind up and become indistinguishable over a few orbital periods. The fact that spiral arms persist despite differential rotation was a recognized problem for decades and required what is called the density wave theory for its resolution. Spiral arms are not fixed collections of stars, but are patterns of density, like traffic jams, through which individual stars pass. The distinction between ordered and disordered stellar motions and different types of galaxies is one of the most diagnostic properties separating spirals from ellipticals. In spiral galaxies, the stellar motions in the disk are predominantly ordered. Stars orbit the center in the same direction with relatively small deviations from circular orbits. This ordered rotation is what the Doppler measurements reveal as a well-defined rotation curve. The ordered motions reflect the disk's origin from a rotating gas cloud that settled into a thin plane as it dissipated energy through gas collisions. In elliptical galaxies, the stellar motions are predominantly random. Stars move in all directions with no preferred orientation, a condition called velocity dispersion support. The elliptical galaxy is held up against gravity not by rotation, but by the pressure of these random stellar velocities. The shape of an elliptical is determined not by a rotation axis, but by the anisotropy of the velocity dispersion. If stars move preferentially in certain directions, the galaxy appears flattened in those directions. Understanding the kinematic structure of elliptical galaxies through spectroscopic measurements of their stellar velocity fields has been one of the major projects of observational galaxy astronomy over the past 2 decades. The orbital structure within a galaxy responds to its history. A merger between 2 disk galaxies converts ordered rotational energy into disordered kinetic energy, producing a remnant that may resemble an elliptical galaxy in its stellar kinematics as well as its morphology. Simulations of disk-galaxy mergers can produce realistic elliptical galaxy kinematic profiles, providing a mechanism for forming the bulk of the elliptical galaxy population through the merging of spirals. The detailed velocity structure, including the presence of kinematic subsystems like kinematically distinct cores, provides information about the specific merger history of individual ellipticals. The density wave theory proposed by C.C. Lin and Frank Hsu in 1964 resolved the winding problem by treating spiral arms not as material structures, but as waves of compression propagating through the galactic disk. In this picture, the spiral pattern is analogous to a traffic jam on a highway. Individual cars pass through the jam and continue on their way, but the jam itself remains stationary relative to the road. Stars and gas clouds enter the arm region, are compressed and slowed as they move through the higher density region, and eventually exit the arm and continue their orbits. The spiral pattern appears stationary because the density wave propagates at a different angular speed from the stars, called the pattern speed, which is intermediate between the orbital speeds of the inner and outer disk. The galaxy merger is one of the most spectacular and one of the most consequential phenomena in the universe, and it is also one of the most poorly intuited because the timescales involved are so far outside human experience that the process seems implausible even to those who understand it intellectually. When 2 galaxies collide, the stars within them almost never physically collide with each other. This sounds paradoxical. If 2 huge systems full of billions of stars come together, how do the stars avoid hitting each other? The reason is the enormous empty space between stars even within a dense galaxy. If the Milky Way's hundreds of billions of stars were all the size of golf balls, the average distance between neighboring golf balls and the galactic disk would be hundreds of kilometers. When 2 galaxies of golf ball-sized stars interpenetrate, the probability that any 2 golf balls actually collide is essentially 0. What the stars do experience is the changing gravitational field as the mass distributions of the 2 galaxies overlap and interact. This gravitational interaction can dramatically alter stellar orbits, flinging stars into new trajectories on time scales of hundreds of millions of years. Gas clouds in the merging galaxies do collide with each other, however, because they are extended structures rather than point masses, and the gas-gas collisions compress the gas, triggering intense bursts of star formation that can produce new stars at rates many times higher than the quiescent star formation in normal disk galaxies. The Milky Way is not immune to this process. It is currently in the process of absorbing the Sagittarius dwarf galaxy, a small galaxy whose stars are being stretched into long streams that wrap around the Milky Way multiple times. In roughly 4 to 5 billion years, the Milky Way will begin a more dramatic merger with the Andromeda galaxy, which is approaching us at about 110 kilometers per second. The collision will reshape both galaxies over hundreds of millions of years, eventually producing a large elliptical galaxy, sometimes called Milkomeda, and will significantly alter the orbits of stars that are currently in both galaxies, including the Sun. The products of galaxy mergers are observable in multiple ways beyond their disturbed morphologies. The burst of star formation triggered by gas compression in a major merger produces a population of young, massive stars that briefly makes the merger remnant extraordinarily luminous at ultraviolet and infrared wavelengths. Ultraluminous infrared galaxies, systems producing 10 to 100 times more infrared luminosity than a normal galaxy, are almost exclusively the products of major mergers in which the starbursts are enshrouded in dust that absorbs the stellar radiation and re-emits it in the infrared. After the starburst fades, the merger remnant often appears as a disturbed elliptical galaxy with the smooth morphology typical of ellipticals, but with subtle features betraying its history. Shells and ripples of stars at large radii that are the remnants of tidal streams from the merging galaxies, stellar streams that have not yet phase-mixed into a smooth distribution. These shells can persist for billions of years and provide a fossil record of the galaxy's assembly history that deep photometric surveys are beginning to characterize systematically. The distinction between major mergers, where two galaxies of comparable mass collide, and minor mergers, where a large galaxy swallows a much smaller one, is important for the resulting dynamics. Major mergers are dramatic and destructive. They reshape both galaxies fundamentally. Minor mergers are gentler. The smaller galaxy is disrupted and absorbed without fundamentally altering the larger one, though it contributes stars to the outer halo and may deposit a minor kinematic signature in the disk. The Milky Way's swallowing of the Sagittarius dwarf is a minor merger. The Milky Way is not significantly disturbed, while the Sagittarius dwarf is completely disrupted. One of the most persistent misrepresentations of galaxies in popular astronomy is the image of them as isolated island universes, floating in the emptiness between them like ships in a vast ocean. This picture captures something real, the enormous distances between galaxies, but it misses the structure that connects them and the physical exchange of material that occurs across those distances. Galaxies exist in groups and clusters, gravitationally bound structures containing between a handful and several thousand members. The Milky Way is a member of the local group, a gravitationally bound collection of approximately 50 galaxies dominated by the Milky Way and Andromeda, with the rest being dwarf galaxies of various types. The local group extends to roughly 10 million light-years in diameter and represents the gravitational island that we inhabit. Beyond the group scale, galaxies and groups are organized into superclusters, enormous structures that span hundreds of millions of light-years. The local group sits at the outskirts of the Virgo supercluster, sometimes called Laniakea, which contains tens of thousands of galaxies and spans roughly 500 million light-years. These superclusters are not simply larger groups. They are not gravitationally bound on their full scale, and the expansion of the universe will eventually pull their more distant members apart. Between galaxies and groups, the space is not empty. It is filled with a diffuse, hot gas called the intergalactic medium, or IgM, whose temperature ranges from millions to tens of millions of Kelvin in the most overdense regions. This gas is far too hot and far too diffuse to be visible in most observations, but it contains a significant fraction of all the ordinary matter in the universe. Galaxies are continuously accreting this gas, which provides the raw material for star formation, and they are continuously ejecting material back into the IGM through stellar winds and supernova explosions. The exchange is not one-directional, it is an ongoing, dynamic cycle. The ram pressure stripping of gas from galaxies moving through a dense intracluster medium illustrates one way that the cluster environment transforms its member galaxies. As a galaxy falls through the hot gas filling a cluster, the pressure of that gas on the galaxy's interstellar medium can exceed the restoring force of the galaxy's own gravity on its outer gas. The result is that gas is stripped from the galaxy, particularly from its outer disk, creating a characteristic jellyfish morphology in which the galaxy trails a wake of stripped gas and newly formed stars behind it. Galaxies stripped of their gas can no longer form stars, and repeated stripping events can quench star formation and transform blue spirals into red lenticulars over time scales of billions of years. The accretion of gas onto galaxies from the intergalactic medium is the complementary process. Cosmological simulations show that gas falls onto galaxies through two distinct channels: a hot mode, in which gas is shock heated to the virial temperature of the dark matter halo, and forms an extended hot atmosphere from which it slowly cools onto the galaxy, and a cold mode, in which cool, dense filaments of gas penetrate through the hot medium and deliver cold material directly to the galaxy's center. The cold mode is thought to dominate in less massive galaxies and at higher redshifts, while the hot mode dominates in more massive galaxies and at lower redshifts. The balance between gas accretion and gas ejection through stellar feedback and AGN-driven winds determines the overall rate at which a galaxy forms stars over cosmic time. Galaxies that efficiently accrete gas and convert it to stars early in their history build large stellar masses early. Galaxies in environments where accretion is suppressed by the hot intracluster medium or by the feedback from their own AGN may be quenched earlier. The specific properties of the local group make it an unusually good laboratory for studying galaxy interactions at close range. The dwarf galaxy population of the local group is extraordinarily well characterized. Individual stars and nearby dwarf galaxies can be resolved, their chemical compositions measured through spectroscopy, and their three-dimensional motions determined through proper motion measurements with the Hubble Space Telescope and Gaia. This level of detail is impossible for dwarf galaxies beyond the local group and provides the most complete picture available of how satellite galaxies form, evolve, and interact with their host. The large-scale structure of the universe, the spatial distribution of galaxies on the largest observable scales, is one of the most remarkable features of the cosmos, and one that was not anticipated from first principles. Understanding it requires stepping back from individual galaxies and looking at the pattern they form across hundreds of millions of light years. When large redshift surveys of galaxies were carried out, beginning in the 1980s, mapping the positions of hundreds and then thousands and then millions of galaxies in 3 dimensions, the pattern that emerged was not the random distribution that an initially uniform universe expanded into, nor the uniform smoothness predicted by simple cosmological models. It was a web, a network of filaments, sheets, and nodes connecting concentrations of galaxies, surrounding enormous voids that contained very few galaxies at all. This cosmic web is not merely the arrangement of galaxies, it is the large-scale structure of dark matter, with galaxies and galaxy clusters forming preferentially at the intersections of dark matter filaments where the density is highest. The dark matter web was laid down in the very early universe, when quantum fluctuations in the density of the primordial plasma were stretched to cosmic scales by cosmic inflation, and then amplified by gravity over the following billions of years. The galaxies are, in a sense, tracers of the dark matter structure, lighting up the peaks while the dark matter dominates the mass. The voids that the cosmic web surrounds are not truly empty. They contain isolated galaxies, diffuse dark matter at below-average density, and the warm, hot intergalactic medium. But their average galaxy density is perhaps 1/10 or less of the cosmic average, creating vast underdense regions that can span hundreds of millions of light years. The largest known void, the Boötes void, is roughly 250 million light years across. A civilization in the center of such a void would see very few nearby galaxies and would have a significantly different cosmological perspective from our own. The voids that make up the majority of the universe's volume by space are not cosmologically unimportant simply because they contain few galaxies. They represent regions where the expansion of the universe is proceeding faster than average, because the density of matter is below average and the decelerating effect of gravity is therefore weaker. The rate at which voids grow and the distribution of their sizes encodes information about the nature of dark energy and the initial conditions of the universe. Void statistics are therefore a cosmological probe complementary to galaxy clustering and the cosmic microwave background. The filaments that connect galaxy clusters in the cosmic web contain a disproportionate fraction of the universe's matter relative to their volume. Gas flows along filaments toward the dense nodes where clusters form, accreting onto galaxies and feeding star formation. The velocity field of galaxies in and around filaments is coherent. Galaxies flow toward the filament axis, and then along the filament toward the nearest cluster. This large-scale velocity coherence is observable as correlated peculiar velocities in galaxy redshift surveys, and encodes the same gravitational information as the spatial clustering. Measuring the cosmic web quantitatively requires characterizing the topology of the galaxy distribution, the network of filaments, sheets, and voids, in a systematic mathematical way. Topological tools from algebraic topology, particularly persistent homology, have been applied to galaxy survey data to extract the network structure of the cosmic web and compare it to predictions from cosmological simulations. These comparisons test the standard cosmological model and constrain the properties of dark matter and dark energy. The classification of galaxies into spirals and ellipticals was one of the early achievements of extragalactic astronomy, and the difference in their appearances was immediately apparent. Spiral galaxies have the pinwheel structure, the blue-tinged arms, the disk morphology that makes them among the most visually striking objects in astronomy. Elliptical galaxies are smooth, featureless, reddish or yellowish in color, roughly egg-shaped, lacking any visible structure. The natural interpretation was that spirals were young, actively forming stars, while ellipticals were old, finished, the dead remnants of a more active earlier phase. This interpretation is half right and half significantly wrong. Elliptical galaxies do have old stellar populations. The dominant stellar content is red giant stars and lower main sequence stars, the survivors of an earlier burst of star formation that occurred in most large ellipticals early in cosmic history, typically within the first few billion years after the Big Bang. The blue color associated with young, hot, massive stars is absent because those stars have long since lived and died. But calling elliptical galaxies dead or passive misrepresents their current state in a significant way. The most massive elliptical galaxies sit at the centers of galaxy clusters and are surrounded by enormous halos of extremely hot gas. This intracluster medium emits X-rays and is the dominant reservoir of ordinary matter in many clusters. As this hot gas cools, it should rain down onto the central galaxy and trigger star formation. But in most cases, star formation rates in these central galaxies are far below what the cooling rate of the gas would suggest. Something is heating the gas, preventing it from cooling. That something is almost always the central supermassive black hole. Even in galaxies whose black holes are not currently accreting at high rates, there is evidence for low-level accretion driving relativistic jets that inflate cavities in the surrounding hot gas, depositing energy that offsets the cooling. This feedback between the central black hole and the galaxy's gas content regulates star formation on cosmological timescales and explains why the most massive galaxies stopped forming new stars billions of years ago. The jets produced by active galactic nuclei in massive elliptical galaxies represent some of the most extreme physical phenomena accessible to astronomical observation. Relativistic jets, beams of plasma accelerated to close to the speed of light and collimated over distances of hundreds of thousands of light years by the magnetic field threading the accretion disk around the central black hole, carry energy from the galactic nucleus to the surrounding intergalactic medium. When these jets terminate, inflating lobes of radio-emitting plasma, they deposit energy in the form of cavities excavated in the hot intracluster gas. These X-ray cavities, visible as surface brightness. Depressions in deep Chandra X-ray observatory images of galaxy clusters are ghost bubbles, regions where the jet plasma has displaced the hot intracluster gas. The work done in inflating the cavities can be estimated from the pressure of the surrounding medium and the volume of the cavity, and this energy input is frequently comparable to the rate at which the hot gas would cool in the absence of feedback. The jets are acting as a thermostat, regulating the temperature of the intracluster medium by injecting energy that offsets radiative cooling. This mechanical heating mechanism, sometimes called radio mode AGN feedback, is one of the most important processes in determining the current state of massive galaxies. Without it, the hot gas in clusters would cool and rain down on the central galaxy at rates that would produce enormous amounts of star formation that are simply not observed. The central black hole, by accreting small amounts of material and launching jets, is preventing the formation of perhaps trillions of solar masses of new stars in the most massive galaxies in the universe. The term active galactic nucleus refers to a phenomenon that was initially cataloged as several separate types of objects before the underlying physical unity was recognized. Seyfert galaxies, discovered in the 1940s, were spiral galaxies with anomalously bright and spectroscopically peculiar nuclei. Radio galaxies, discovered when radio astronomy became possible after World War II, were galaxies emitting enormous power at radio wavelengths, often with jets extending hundreds of thousands of light years into the surrounding space. Quasars, discovered in the 1960s, appeared initially as point sources of light resembling stars, but showed enormous redshifts indicating extreme distances and thus luminosities that no stellar model could explain. The unification of these varied phenomena under the single explanation of matter accreting onto a supermassive black hole was one of the major theoretical achievements of 20th century astrophysics. In the AGN model, material spiraling into a supermassive black hole forms an accretion disk that can radiate with extraordinary luminosity. The energy efficiency of accretion onto a black hole, meaning the fraction of infalling mass energy that is radiated away, is roughly 10% for standard accretion processes, compared to less than 1% for nuclear fusion. This makes accreting black holes the most efficient energy sources in the universe. The apparent variety of AGN types arises partly from real differences in accretion rate and partly from orientation effects. The same type of object looks different depending on the angle from which it is observed. An AGN viewed along the axis of its jet looks like a blazar, one of the most luminous and rapidly variable objects known. The same object viewed from the side shows a Seyfert galaxy or radio galaxy appearance depending on the radio power of the jets. This unified model, proposed in the 1980s and confirmed by subsequent observations, explained the diversity of AGN types as aspects of the same underlying phenomenon. The luminosity function of AGN, the distribution of how many active galaxies exist at each luminosity level, is a steep function. For every AGN 100 times more luminous than average, there are many more less luminous ones. This means that while the most luminous quasars are the most spectacular and were the first to be discovered due to their visibility at cosmological distances, the bulk of the integrated AGN luminosity over cosmic history comes from more numerous lower luminosity systems. Understanding the AGN phenomenon requires characterizing this full population, including the faint, obscured, and low luminosity AGN that dominate by number. The relationship between supermassive black hole mass and the properties of the host galaxy bulge is one of the most significant discovered in modern extragalactic astronomy. Studies in the late 1990s revealed that the mass of the central black hole correlates tightly with the velocity dispersion of stars in the host galaxy's bulge, a measurement that reflects the total mass of the bulge. The relationship is remarkably tight, given that the black hole's sphere of influence is vastly smaller than the bulge. The black hole affects stellar dynamics only within a few light years, while the bulge extends thousands of light years. Yet somehow, the total mass of the black hole knows about the total mass of the bulge. This scaling relation implies that black holes and their host galaxies grew together through a process in which each regulated the other's growth. When the black hole mass became large enough relative to the bulge mass, AGN feedback heated and expelled gas, suppressing further star formation in the bulge. When the star formation was suppressed, less gas funneled to the center, reducing the AGN activity. This co-evolutionary framework, in which black holes and galaxies grow and self-limit together, is the current theoretical framework for understanding the mass-ratio relationship. The discovery of quasars in the early 1960s produced one of the deepest puzzles in the history of astronomy and, when resolved, provided one of the most consequential insights about the nature of galaxies and cosmic history. The story is worth telling in some detail, because it illustrates how genuinely unexpected the universe can be, even when observations are being made by the most skilled practitioners with the best instruments of their era. When radio astronomers in the late 1950s began identifying the optical counterparts of strong radio sources, several appeared to be ordinary stars, compact objects showing no detectable nebulosity. Spectroscopy of these objects, expected to show stellar spectral features, instead showed something completely unfamiliar: bright emission lines at positions that did not match any known atomic transitions. In 1963, Martin Schmidt, working at the California Institute of Technology, realized that the spectrum of 3C273, one of the brightest radio sources identified with an apparent star, showed the hydrogen-Balmer series emission lines, but shifted to the red by 16% in wavelength. A redshift of 16%, if cosmological in origin, placed 3C273 at roughly 2 billion light-years from Earth. At that distance, to appear as bright as it did in the sky, 3C273 had to be radiating energy at a rate of roughly 10 trillion times the Sun's luminosity, comparable to hundreds of entire galaxies. And it was varying in brightness on timescales of weeks, which constrained its physical size to be smaller than light weeks across. Something smaller than the solar system was outshining hundreds of billions of stars. What quasars revealed was that the early universe was an era of intense activity. The redshift distribution of quasars shows that they were far more common billions of years ago than they are today. The quasar era, centered around 10 billion years ago, when the universe was roughly 3 billion years old, was a time when the supermassive black holes at the centers of forming galaxies were accreting material at their maximum rates, shining with luminosities that could be detected at cosmological distances. Understanding quasars means understanding the early universe and the role of black hole growth in shaping the galaxies we see today. The host galaxies of quasars provide direct evidence for the connection between AGN activity and galaxy evolution. When the light of the central quasar is suppressed or subtracted, the surrounding galaxy becomes visible, and these host galaxies are often found to be undergoing major mergers. The morphological disturbances, tidal tails, and double nuclei typical of galaxy mergers are seen around many high-luminosity quasars, consistent with the picture that major mergers funnel large amounts of gas to the galactic center, feeding the supermassive black hole at rates that produce quasar luminosities. The spectra of quasars are also extraordinarily rich in astrophysical information. Quasar spectra contain absorption lines produced by intervening gas clouds at various redshifts along the line of sight, and the pattern of these absorption lines is called the Lyman alpha forest. Each absorption line corresponds to a cloud of neutral hydrogen at a specific redshift, and the forest of lines maps the distribution of diffuse gas throughout the intergalactic medium at different cosmic epochs. The Lyman alpha forest has been used to measure the distribution of matter at high redshift, constrain the thermal history of the intergalactic medium after the epoch of Ryanization, and probe the large-scale structure of the universe at epochs inaccessible to galaxy surveys. The highest redshift quasars yet discovered, at redshifts above 7, corresponding to when the universe was less than 1 billion years old, present a significant puzzle. They host black holes of several billion solar masses that somehow assembled in a very short time after the Big Bang. The standard models of black hole growth through accretion, even operating at the maximum theoretically allowed rate, struggle to produce such massive objects this early. The existence of these high redshift monsters requires either exotic early seeding mechanisms, extended periods of super-Eddington accretion, or both. The James Webb Space Telescope, launched at the end of 2021 and reaching operational status in 2022, was designed in part to observe galaxies in the earliest accessible epochs of cosmic history, when the universe was only a few 100 million years old. The expectation, based on the standard model of galaxy formation, was that the universe at those early times would contain the raw material of galaxies, diffuse gas clouds beginning to collapse, small dwarf galaxies in the process of forming, the seeds of the large structures we see today. What JWST found instead was genuinely surprising and has generated significant scientific debate. Among its early discoveries were galaxies that appeared unexpectedly massive and unexpectedly well-formed for their cosmic age. One candidate, designated JWST-ER1G, appeared to have a stellar mass comparable to the Milky Way at a redshift, corresponding to when the universe was less than 1 billion years old. Several others showed mature morphological features, disk structures, and bulges at epochs when galaxies were expected to be still forming and highly irregular. These early results do not necessarily require abandoning the standard cosmological model, but they require that it be refined. Either these galaxies formed their stars with extraordinary efficiency compared to what is observed in nearby galaxies, or the initial mass function of stars in early galaxies was different from the local one, producing more luminous stars per unit of stellar mass, and therefore making galaxies appear more massive than they are. Or there are other systematic effects in the observations that have not yet been fully characterized. The early galaxy problem is still being actively worked on, and the ultimate resolution will require both more JWST observations and more detailed theoretical modeling. But it illustrates a point central to tonight's topic. Galaxies are not what they seem even to the theorists who build the models. The universe keeps finding ways to produce structures that exceed naive expectations. The discovery of massive, compact, quiescent galaxies at redshifts of 2 to 3, when the universe was roughly 2 to 3 billion years old, was an early indication that something in the standard picture of galaxy formation needed revision. These galaxies, containing as much stellar mass as today's most massive ellipticals, but compressed into much smaller volumes, were dubbed red nuggets. Their compactness meant that the massive elliptical galaxies we see today could not simply be evolved versions of these early compact systems. The ellipticals are much larger in physical size despite having similar stellar masses. Something must have happened between the compact high redshift phase and the extended low redshift state. The proposed mechanism for the size growth is minor mergers. The accretion of small satellite galaxies over billions of years adds stellar mass primarily to the outer regions of the galaxy, increasing the effective radius without dramatically changing the overall stellar mass. This inside-out growth mechanism predicts that the cores of today's massive ellipticals preserve the properties of the high redshift compact systems, while the extended envelopes were built up through subsequent accretion. The stellar population gradients observed in nearby ellipticals, with older, metal-rich stars in the center and younger metal-poor stars in the outer parts, are qualitatively consistent with this picture. The JWST discoveries of apparently massive, well-formed galaxies at even higher redshifts than the red nuggets add additional pressure on the standard model. If confirmed, these early massive galaxies imply that the process of galaxy formation was faster and more efficient in the early universe than current simulations generally predict. Whether this requires new physics, revisions to the initial mass function of early stars, or improved treatments of feedback processes within existing physical frameworks is the subject of intense current research. The velocity dispersions of the compact massive galaxies at high redshift, measured through spectroscopy of absorption lines in their stellar spectra, are consistent with the high central stellar densities implied by their small sizes and large stellar masses. These galaxies are genuinely compact and not merely artifacts of observational limitations. Understanding why the universe formed such compact massive systems early, and then built extended structures around them rather than forming extended systems from the start, is central to understanding the physics of galaxy formation. The ordinary matter in the universe, the matter made of protons, neutrons, and electrons that constitutes all the familiar material objects, is called baryonic matter by cosmologists, a term derived from the baryon class of particles that includes protons and neutrons. The total density of baryonic matter in the universe is determined with good precision from measurements of the cosmic microwave background and from the abundances of light elements produced in the first few minutes after the Big Bang. These constraints agree. Baryons constitute roughly 5% of the total energy content of the universe, with dark matter making up another 27%, and dark energy the remaining 68%. The problem is that when astronomers actually look for the baryons in stars, in interstellar gas, in galaxy clusters, they can only find roughly half of them. The other half, roughly half of all the ordinary matter in the universe, appears to be missing. It cannot be in the form of dark matter because the evidence for baryonic and non-baryonic dark matter are independent. It cannot have been converted to radiation or otherwise destroyed because boron number is conserved. It must be somewhere, in some form, but not in the forms that the surveys have found it. The current best candidate for the missing baryons is the warm-hot intergalactic medium, the Wi-Shi-M, a diffuse filamentary gas at temperatures between 100,000 and 10 million Kelvin that pervades the large-scale structure of the universe. At these temperatures, the gas is too hot to emit much optical or ultraviolet light, but produces faint X-ray emission and absorption signatures against background quasar spectra. Several observational programs have found evidence for this gas, and the leading interpretation is that the missing baryons are distributed through the cosmic web in this diffuse, difficult-to-observe form. But the census is not complete, and the missing baryon problem remains one of the significant open questions in observational cosmology. The temperature range of the warm-hot intergalactic medium makes it particularly challenging to observe. Gas at temperatures between 100,000 and 10 million Kelvin emits primarily in the extreme ultraviolet and soft X-ray bands. Earth's atmosphere absorbs these wavelengths, so observations require space-based telescopes. At these temperatures, hydrogen and helium are fully ionized and cannot produce the ultraviolet absorption lines used to detect cooler intergalactic gas. The primary observational signature is X-ray emission from thermally excited ions of oxygen, neon, and other metals, and absorption of background radiation by these same ions. Several programs using the X-ray observatories Chandra and XMM Newton have detected emission from the warm-hot intergalactic medium in filaments connecting galaxy clusters, providing the most direct confirmation that this gas exists in the densities required by the missing baryon estimates. The detections are at the edge of current instrument sensitivity and are subject to systematic uncertainties. But the ensemble of evidence is now persuasive that the filamentary cosmic web contains the bulk of the missing baryons. The Sunyaev-Zeldovich effect, which describes the scattering of cosmic microwave background photons by hot electrons, has also been used to detect warm gas in the cosmic web between galaxy pairs and in groups. By stacking the CMB maps over large numbers of aligned galaxy pairs and measuring the average temperature decrement along the connecting axis, researchers have detected the signature of hot gas in the intergalaxy region. These statistical detections suggest that the filaments connecting galaxies contain significant gas masses that account for a substantial fraction of the missing baryons. The color of a galaxy, whether it appears blue, red, yellow, or green, is one of the most immediately apparent properties visible in galaxy images, and one of the most routinely misinterpreted. The color encodes information about the stellar population, the dust content, and the distance of the galaxy, but not in a straightforward way that allows simple visual interpretation. The fundamental issue is that galaxy colors result from the integrated light of billions of stars in different evolutionary stages, modified by dust absorption and by the cosmological redshift that shifts all wavelengths toward the red proportional to distance. Disentangling these effects requires detailed photometric or spectroscopic analysis rather than simple color inspection. Blue color in a galaxy typically indicates ongoing star formation, massive, hot. Blue stars form in great numbers in star-forming regions and dominate the integrated light, making the galaxy appear blue. But blue color can also indicate a recent burst of star formation that has since ended, because the hot blue stars fade on time scales of tens to hundreds of millions of years after star formation stops. A galaxy that stopped forming stars 50 million years ago can still appear blue. Red color typically indicates an old stellar population dominated by red giant stars. But it can also indicate a young stellar population heavily obscured by dust, which absorbs the blue light preferentially and makes the galaxy appear red even if it is actively forming stars. Some of the most intensively star-forming galaxies in the universe, the ultraluminous infrared galaxies where star formation is occurring at rates hundreds of times the Milky Way's rate, appear red or even invisible in optical surveys because they are so heavily dust-enshrouded. Green galaxies, a category that sits between the blue star-forming sequence and the red passive sequence in color magnitude diagrams, were initially thought to represent an intermediate evolutionary stage, galaxies in the process of transitioning from active star formation to quiescence. More detailed analysis has revealed that green galaxies are a heterogeneous category, including some genuinely transitioning systems, but also dust red and blue galaxies and recently quenched red galaxies that still retain some residual star formation. The ultraviolet upturn in elliptical galaxies illustrates a particularly striking case of color-deceiving interpretation. Many old elliptical galaxies that appear uniformly red in optical images show unexpected ultraviolet emission, a blue excess relative to what models of purely old stellar populations predict. For decades, this was mysterious because the same stellar evolution models that correctly predicted the red optical colors of old stellar populations failed to account for the UV emission. The resolution came from understanding that very old metal-rich stars can evolve in a way that produces hot horizontal branch stars, even without recent star formation. Helium-burning stars that have shed most of their outer envelopes and become unusually hot. The UV upturn in old ellipticals is thus a signature of old age and high metallicity rather than youth, the opposite of what UV emission in other contexts implies. The Green Valley, the region between the blue star-forming main sequence and the red passive sequence in the color magnitude diagram of galaxies, was originally interpreted as a sparsely populated transition zone. The reasoning was straightforward. If galaxies transition from active to passive state over a relatively short time, they should spend relatively little time in the intermediate color range, so the Green Valley should be underpopulated. While this is broadly correct, the interpretation of individual Green Valley galaxies is complex. Detailed spectroscopic analysis reveals that the Green Valley is populated by galaxies with a wide range of current star formation rates, specific ages, and dust contents that scatter into the intermediate color region from both the blue and red sides of the distribution. The realization that photometric color is a poor proxy for current star formation rate in individual galaxies because of the degenerate contributions of age, metallicity, and dust has driven the development of more sophisticated analysis techniques, fitting spectral energy distributions to model stellar populations using Bayesian inference methods, incorporating constraints from emission, line diagnostics of ionized gas, and combining photometric and spectroscopic information are now standard approaches for extracting reliable star formation rates and stellar masses from galaxy observations. The infrared emission from galaxies traces the re-radiation of absorbed ultraviolet and optical light by dust, providing a measure of star formation that is immune to the dust attenuation that makes optical measurements uncertain. Infrared surveys have revealed a population of dusty star-forming galaxies at cosmological distances, particularly luminous and ultraluminous infrared galaxies that were largely missed by optical surveys. These galaxies contribute significantly to the cosmic star formation rate density at redshifts of 1 to 3, the peak of cosmic star formation activity, and their discovery required infrared space observatories to see through the dust that hides their activity at shorter wavelengths. The gravitational physics that holds a galaxy together and gives it its structure is not primarily the gravity of the stars we see. Stars contribute about 10 to 20% of the total gravitational field that governs stellar orbits. The rest comes from dark matter, and, in gas-rich galaxies, from the interstellar gas. Understanding galaxy dynamics without including dark matter produces predictions that are drastically wrong in every observable consequence. The rotation curves are wrong, the velocity dispersions of stars are wrong, the stability conditions for disk fragmentation are wrong, and the gravitational lensing properties are wrong by factors of several. The dark matter halo is not merely a gravitational container for the visible galaxy. Its structure, density profile, and response to the presence of the stellar and gaseous components shape the visible galaxy in specific ways. The concentration of the dark matter halo, measuring how centrally condensed it is, determines the strength of the gravitational potential in the inner galaxy, and influences how the stellar disk forms and evolves. Simulations of galaxy formation that include realistic dark matter halos can reproduce the observed properties of disk galaxies, including the formation of bars and spiral arms, in ways that simulations without dark matter cannot. The interaction between the dark matter halo and the baryonic matter it contains is bidirectional. Dark matter shapes the distribution of stars and gas, but the presence of a massive concentration of baryons in the center of the halo can modify the dark matter distribution through a process called adiabatic contraction. As the stellar disk forms and the baryons sink to the center, the dark matter responds to the deepening gravitational potential by concentrating toward the center as well. In extreme cases, the energetic feedback from stellar winds and supernovae can expel gas from the center, causing the dark matter to expand and form a core rather than a cusp in its central density profile. The response of the dark matter halo to stellar feedback represents one of the significant open questions at the intersection of dark matter physics and galaxy formation. In dwarf galaxies, where star formation can occur in concentrated bursts powerful enough to drive the bulk of the gas from the galaxy, in a short time, the rapid expulsion of gas reduces the gravitational potential at the center of the dark matter halo, and the dark matter particles that were orbiting in response to that potential expand outward as the potential decreases. This repeated cycle of gas infall, starburst, and outflow can gradually transform an initially cuspy dark matter density profile, one that rises steeply toward the center, as predicted by pure dark matter simulations, into a chord profile with a roughly constant central density. Whether this feedback-driven core formation process operates at the required level in real galaxies is a subject of active investigation. The observations of dark matter density profiles in dwarf galaxies, inferred from the orbital velocities of stars, are consistent with chord profiles in some cases and cuspy profiles in others, and the observations themselves carry systematic uncertainties related to the non-spherical shapes of real dwarf galaxies. The theoretical models require specific conditions of star formation history and feedback efficiency for core formation to occur. The dark matter halo also plays a role in determining which small structures become visible galaxies and which remain dark. Cosmological simulations of structure formation in cold dark matter universes predict many more small dark matter halos than there are observed satellite galaxies around the Milky Way. This discrepancy, called the missing satellite problem, can be resolved if most small halos never form significant numbers of stars, either because reionization heating prevents gas from cooling in the smallest halos, or because supernova feedback expels the gas from small halos early in their history. The dark matter halo mass determines whether a dark matter structure becomes a visible galaxy or remains a dark subhalo. Having dismantled the various misconceptions about what galaxies are, it is worth assembling a more accurate picture of the full composition of a typical massive galaxy like the Milky Way. What is actually there, in what proportions, and how do the various components relate to each other? Dark matter constitutes roughly 80 to 90% of the total mass of the Milky Way system. It is distributed in a roughly spherical halo, extending to roughly 600,000 to 1 million light-years in radius, with a density that decreases with radius approximately as 1 over radius squared, or radius cubed in the outer halo. The dark matter halo is the dominant gravitational structure within which everything else resides. Stars constitute roughly 5 to 7% of the total mass, or about 50 to 60 billion solar masses for the Milky Way. They are concentrated in the disk, the central bar, the bulge, and the stellar halo, spanning a range of ages from very old stars formed 12 or 13 billion years ago to the youngest stars formed within the past million years. The stellar mass-to-light ratio, how much mass each unit of luminosity represents, varies across the galaxy depending on the age and chemical composition of the stellar population. Interstellar gas, primarily hydrogen and helium in molecular, atomic, and ionized phases, constitutes roughly 1% of the total mass. The gas is the raw material for ongoing star formation and is concentrated in the disk, particularly in the spiral arms where molecular clouds have formed. It is continuously being consumed by star formation and replenished by stellar mass loss and infall from the circumgalactic medium. Interstellar dust, tiny solid particles of silicates and carbonaceous compounds, constitutes a fraction of 1% of the total mass, but has a profound effect on observations because it absorbs and scatters light efficiently, obscuring large fractions of the galaxy at optical wavelengths. The circumgalactic medium, a diffuse halo of hot and warm gas extending to hundreds of thousands of light years, contains roughly as much mass in gas as the stellar disk contains in stars. It is the reservoir from which the galaxy draws fuel for star formation and the sink into which the galaxy ejects material through outflows. It is practically invisible in most observations, but has been detected through absorption features in the spectra of background quasars and through faint X-ray emission. The stellar populations within the Milky Way carry a chemical record of its formation history, encoded in the abundance patterns of individual stars. The oldest stars in the galaxy, in the thick disk and stellar halo, were enriched by the products of core collapse supernova from the first generation of massive stars, giving them characteristic abundance ratios of alpha elements like oxygen, magnesium, and silicon relative to iron. Younger thin disk stars formed after Type 1. A supernovae had had time to enrich the interstellar medium with iron, show lower alpha to iron ratios. This chemical bimodality of disk stars, confirmed by large spectroscopic surveys including APOG, traces the history of star formation and enrichment across different epochs of the galaxy's life. The hot phase of the Milky Way's interstellar medium, gas heated to millions of degrees by supernova explosions and stellar winds, fills a significant fraction of the disk volume. This hot gas is in constant exchange with the colder phases. Supernova remnants sweep up cold gas, compress it, and eventually cool. Cooled gas collects into molecular clouds that form new stars. Those stars eventually explode and reheat the gas. This cycle of heating and cooling, regulated by stellar feedback, determines the interstellar medium's multi-phase structure and the overall efficiency with which galaxies convert their gas to stars over cosmic time. The magnetic field permeating the interstellar medium is an often neglected component of galactic structure. The Milky Way's large-scale magnetic field is organized along the spiral arms, with a field strength of roughly a few microgauss, comparable to the equipartition strength with cosmic rays and turbulent gas pressure. This magnetic field is not a passive observer of galactic dynamics. It contributes to the pressure support of the interstellar medium, regulates the rate at which molecular clouds collapse to form stars, and channels the transport of cosmic rays along field lines. Understanding the role of magnetic fields in galaxy evolution is one of the research frontiers where observational capabilities have been improving rapidly through radio polarimetry surveys. The picture of galaxies that has emerged from a century of increasingly powerful observation and theory is one that would have been essentially unrecognizable to the astronomers who first cataloged the nebulae and first measured the distances to the nearest ones. The visible galaxy, the pinwheel of stars that produce the wonder and the photographs, is a small, bright, active component sitting inside a much larger invisible structure. The dark matter halo is not a theoretical artifact or a convenient addition to make calculations work. It is the primary gravitational entity, the structure within which stars and gas are organized into the objects we actually observe. The dynamic history of galaxies, their mergers, their quasar phases, their regulation by central black holes, their continuous exchange of material with the intergalactic medium, Their organization within a cosmic web of dark matter filaments is a complete departure from the static, bounded picture that seemed adequate when galaxies were first understood to be external star systems. None of this makes galaxies less magnificent. The spiral arms, when understood as density waves rather than fixed stellar structures, are more impressive in their physical subtlety. The quasar, when understood as matter falling into a black hole with an efficiency far exceeding nuclear fusion, is more remarkable in the physics it involves. The cosmic web, when understood as the gravitational inheritance of quantum fluctuations from the universe's first fraction of a second, is more philosophically resonant than the simple scattering of point-source galaxies in empty space. The deep lesson from the study of galaxies is one that recurs throughout the history of astronomy. What you can see is never the whole story. Every time astronomers have extended their reach to new wavelengths, new distances, or new sensitivity limits, they have found that the universe is structured differently and typically more richly than what was visible before. Dark matter was invisible until rotation curves made it necessary. The cosmic web was invisible until redshift surveys made it unavoidable. The circumgalactic medium was invisible until quasar absorption spectra made it undeniable. Galaxies appear, in ordinary images, as self-contained, bounded, isolated things. They are none of those things. They are open systems embedded in larger structures, shaped by invisible mass, animated by the physics of their central black holes, and connected to each other through a web of dark matter and hot gas that spans the observable universe. The image in the textbook is real. It is just the beginning. The recurring theme of invisible components dominating visible ones is not merely a technical curiosity about measurement limitations. It speaks to something fundamental about how we construct knowledge of the universe. We begin with what is visible, what produces photons our instruments can detect. We build models to explain the visible. Those models make predictions about what else should be there, often in forms we cannot directly see. When we find ways to test those predictions, we discover that the invisible, the dark matter, the hot gas, the circumgalactic medium, the magnetic fields, the cosmic web structure, is often more important to the system than the visible component that first drew our attention. The history of science more broadly follows a similar pattern. The visible phenomena we study directly are rarely the fundamental ones. Thermodynamics preceded atomic theory, genetics preceded molecular biology. The map of what is observable at any given moment underrepresents the territory of what matters causally. Galaxies have been a particularly vivid demonstration of this principle because the invisible component is not merely important, but dominant. 5 to 10 times as massive as everything that produces light. Galaxies are also windows. Each one is a sample of the universe's content at its particular location and at the cosmic time corresponding to its distance. Since light takes time to travel, distant galaxies show us what galaxies looked like billions of years ago. The collection of all observable galaxies is therefore a four-dimensional archive, a database of cosmic history encoded in light that has been traveling for different fractions of the universe's age. Reading that archive is the project of modern extragalactic astronomy, and the reading reveals not just what galaxies are, but what the universe was and how it became what it is. What galaxies actually are, in the full picture that astronomy has assembled over a century of progressively deeper observation, is something genuinely extraordinary. The visible nodes of an invisible web, shaped by physics operating from quantum to cosmic scales, connected across vast distances by the same processes that govern the smallest structures, carrying the chemical history of everything from the Big Bang to the present. The image in the photograph is beautiful. The full reality is more beautiful still.